You ready?
Yeah.
Okay. Last time we didn't talk about the first point here, but let me just point it out that all materials have imperfections. And if we're talking structural materials, we're interested in imperfections bigger than the atomic scale. If you're talking functional materials like photonic or electronic materials, you may be interested in the imperfections on an atomic scale. An actual vacancy or a substitutional atom in a silicon or something will control the functional properties. But the structural properties, it's those little notches like in the piece of paper that control the properties. I looked for an overhead, another quote from Bob Sprague. I couldn't find it this morning, but basically the quote, Bob Sprague was the head of materials at General Electric Aircraft Engines, and he says, material scientists think that structure controls properties. And if you actually happen to be a material scientist for years, ever since I was a student, they said structure properties performance, okay? Or then processing structure properties performance. Anyway, Bob Sprague says, material scientists think that structure determines properties, but metallurgists know that defects control properties. And in fact, for structural materials, it is the flaws that are going to control the properties. And in fact, fracture mechanics tells us that the stress intensity, which is what's going to make the crack grow, is equal to the stress times the square root of the crack length. And there's all kinds of different geometries you have to go in that. There's different stresses because you can have tensile stresses, you can have shear stresses, and the fracture mechanics calls that mode 1 for tensile, mode 2 for, turns out it's in-plane shear, and mode 3 for out-of-plane shear. We don't have to go through all that. But fracture mechanics, using that basic equation of stress intensity is equal to the stress times the square root of the crack length, basically tells you whether the crack's going to propagate under different conditions. Now, a lot of people don't believe that there are flaws in parts. One of the stories I heard from the Air Force once is the U.S. Air Force was doing research trying to see if they could use acoustic emission to see if cracks were propagating in an aircraft. And so they, acoustic emission is basically just putting a very sensitive microphone, essentially a piezoelectric transducer, that can go into the megahertz regime, and just listening for vibrations, sound waves that come through the material. It doesn't have to be audible sound. It can be megahertz, well beyond your ear, but you can measure if anything's vibrating at very high frequency in the part. And people try to use acoustic emission. The real problem with acoustic emission is there's a lot of other sources of acoustic emission or noise. If two parts slide against each other, they'll generate noise. And it's not necessarily just cracks opening up. But in any case, this was about 10 or 20 years ago. The U.S. Air Force decided they wanted to intentionally put a known size flaw in the structure of an aircraft and fly it and use the sensor to see if they could detect the crack growing. And what happened was some general says they actually ended up having to fly it in an Australian aircraft because a general in the U.S. Air Force said, well, you're not going to put a crack in one of my airplanes, okay? Because the general didn't understand. Boeing finds cracks in aircraft that have never even gotten out of the plant. Okay? If you actually went to an automobile or a plane, you would probably find dozens. If you did a very thorough inspection, you would probably find dozens of small flaws. Fortunately, if the material is ductile, it will be resistant. We're going to talk today about fatigue. It will be resistant to the propagation of the crack. If it has a lot of fracture toughness, remember that it's only when the stress intensity, K, becomes greater than the fracture toughness, K, of the material, that the crack is going to propagate catastrophically. And so if you have a high toughness material, it's hard to propagate cracks. And so you can tolerate big flaws. Generally, on a very crude scale, fracture can be divided into fracture above the yield stress, which we call overload, and fracture below the yield stress, which are all kinds of types of fracture. There hasn't been a lot of study on overload fracture because we can calculate that. People could calculate that in the 1880s, just force per unit area. Is it above a certain value of yield stress or not? And if we were talking about a ductile metal, you can see the parts stretch and deform before the thing breaks. It was overloaded. However, there's lots of other types of fracture which people spend lots of time studying because it's much more insidious. You've designed the part and you don't expect it to fracture. Overload, hey, if you'd done your calculation correctly to begin with, you would have known it. But if we're dealing with fracture below the yield stress, that often comes as a big surprise, and the real problem is when you have a big surprise. In fact, in the area of fracture studies, there's a number of approaches to fail-safe design. I mean, you can just spend a huge amount of money and make sure that the thing is so big and so heavy that it'll take any stresses that can be given to it. And that's the approach a lot of people want to take to, why did the World Trade Center fall down? Well, it wasn't built well enough. Well, that's rubbish, okay? You could build a building that would survive that fire, and certainly that building survived the impact of the aircraft. It was strong enough to do that, which if you read the article I gave you, I think it was in your packet. You know, if you actually think about it, the building weighed, what, 500,000 tons, and the aircraft weighed 200 tons. So when you hit, you know, a huge object, 500,000 tons with a little bitty object of 200 tons or whatever, then, you know, it just kind of bounces off. In this case, it didn't exactly bounce off. It went into it. They all fractured together. But the building didn't fall down because it got hit. It's kind of like shooting a BB at a bowling ball. You know, the BB is not going to move the bowling ball very much. Well, people say, well, why didn't we build the building better so it would have survived this? We could build all our buildings so they would survive a terrorist attack of a jet. I mean, Saddam Hussein built hardened bunkers, right? That we had to build special bombs to try to penetrate, you know, 100 yards into the earth to try to destroy. It cost a lot more money to build that building. So if we want 75% of our population to, you know, live in tents and cardboard huts, so that the other 25% of the population can live in a building that's safe from a terrorist attack, we could do that. But you have to, there's a balance, economic balance here, between building something that's practical and functional and will survive most things that will be thrown at it, as opposed to building everything like it's a bunker to survive a terrorist attack. But that's just philosophy of things, of how safe is safe enough. And the problem is, whenever anything happens, people think, oh, it's not safe, just like the general who wouldn't fly his aircraft with a crack. Don't tell him he's got a couple of thousand cracks in every one of his aircraft, because he may not be very happy. In any case, let me start talking a little bit about fatigue. Prior to about 1950 and 1960, the traditional view of fatigue was what's called an SN curve, S for stress and N for number of cycles. And the SN curve basically plots on a log scale, a semi-log scale on the bottom for number of cycles, and the stress here. And over here, at one cycle, is what you call the yield stress of the material, uniaxial yield stress or tensile stress of the material. It will break at the tensile stress, it'll deform at the yield stress. Well, if you take a paper clip and you just vibrate it, or if you bend it back and forth, you're doing what's called low cycle fatigue. Somewhere between 10 and 100 cycles, the thing will break at a stress less than it would on a single cycle. And if you go out and you actually set up a machine and you vibrate that thing 100,000 times or 1,000,000 times, it will break at a still lower stress. And the curve typically comes down and then runs across fairly flat. There'll actually be data points. This is actually showing you there's a fair amount of scatter. On life, a factor of 10 on life may only be about a factor of 30% on stress. Okay, if you look at the kind of error bands on these typical types of plots. But basically, people just they might take a bar of material and they put it in a machine, a lot of times just one's a rotating beam machine, and basically just vibrate it back and forth a few million times. You can go out, typically these things go out to about 10 million cycles. Sometimes they go to 100 million cycles. Anybody know why we don't go even further out? Because how many seconds are there in a year? It turns out there's 3 times 10 to the 7 seconds in a year. And so if you're running your cycles at 1 per second, it takes you 4 months to run a test to get one data point. And that gets a little pricey when you go way out here. There are people who've done 10 to the 8th cycles, and a very few samples where people have done 10 to the 9th, but that's when they're putting in a special machine and vibrating at 100 hertz or even 1,000 hertz. Well, you run into problems there in your testing because you can overheat the sample just because you're putting enough mechanical work in it that it can heat up. And so now you're not doing a room temperature test anymore. So you run into limits as you go through things. There is something, well, actually, this first part of the curve is generally called the plastic region, where it slopes. And somewhere between, around, let's say, 10 to the 4th and 10 to the 5th, sometimes 10 to the 3rd, 10 to the 5th, you will have a transition from plastic behavior to elastic behavior. So if you take the paper clip and you bend it and it stays bent, you're going to be in what's called low cycle fatigue down here, below about 100,000. If you go above, you can actually take it like a diving board, and you can stress it, but it springs right back to its original position. So that's elastic fatigue over here. High cycle elastic fatigue, lower stress, low cycle plastic fatigue. The problem with most things is we try to design them to be out here in the elastic region. You don't want a part that's going to deform every time you bend it, every time you load it. So you design it out here, and sometimes they still fail. Well, why do they still fail when they're in the elastic region? Well, sometimes people talk about damage accumulation in the part. Okay, and if you go look microscopically, you can see when you're vibrating out here, you find microscopically little regions where the dislocations in this crystal and stuff will actually start little flaws. And you actually are creating little notches. And those little notches get to be bigger notches. And as they get to be bigger notches, it turns out fracture mechanics is going to tell you that the stress intensity increases. If the stress intensity increases, that crack's going to start growing faster and faster. Well, what people learned when they started doing fracture mechanics, they said, this should be able to be applied to fatigue as well. And I'm going to show you what happened in around 1960s. People started going to a new way to look at fatigue. But before we do that, there was one other thing. Oh, when you do this type of fatigue, you take a sample and you just vibrate it enough times until it breaks completely in two. Well, you don't need to know that. And you shouldn't have to necessarily do 10 or 20 different specimens. So that gets expensive in material and machining and test time and everything else. There's lots of specimens it takes at least 10, if not 20 specimens to generate one of these curves. Another thing that people have found, at least for steels, is there's something called a fatigue limit. And they define the fatigue limit as the stress below which you don't expect to find fatigue. And we often talk about fatigue limits because steel has a fatigue limit. You will, at 40 to 50%, around half of the yield stress, and if you kind of follow this guy over, it's somewhere just below 50%, but somewhere, depending on the strength of the steel, between 40 and 50%, you'll hit the fatigue limit. And you essentially, if you design things properly, your material is immune to fatigue below the fatigue limit, if it's steel. Aluminum does not have a fatigue limit. Why? Well, there's lots of reasons, but basically aluminum being more reactive gets a little bit of surface damage and it oxidizes and things. But aluminum, this thing will still have a very, very slow slope. A number of years ago, they wanted to, if you can make something lighter, remember the faster something moves, or the longer you use it, the more important lightweight is, they wanted to use aluminum wheels on trucks. The problem with trucks, I mean, we've been using aluminum wheels on cars for years. You go back 40 or 50 years and you make aluminum wheels for cars and put the tire on this aluminum wheel. Well, they wanted to do it for trucks, and they tried it in the 1970s, and they tried cast wheels, forged wheels, best quality aluminum they could get. The problem is, for trucks, which might go 1,000,000 miles, and now you're talking about 10 million or 100 million cycles over a 10 or 15-year period on something that doesn't have a fatigue limit, they were having a hard time not having one of these things break apart. And when they develop cracks and break apart, it's not a good day necessarily for the truck driver. So they now have aluminum wheels for trucks, and they've improved some of the design and stuff, but it's still, you wanted aluminum wheels for trucks because, again, if you're going a million miles, you actually might be talking about a value of $10 or $15 per pound saved over the life of that vehicle. Remember, it's $2 for a car. Well, a truck that goes 10 times as far ought to be something on the order of 10 times the savings in terms of gas for a pound saved. So people tried to do it, but because aluminum doesn't have a fatigue limit, they had some problems, and they have resolved some of those. But if I go to fracture, people started thinking about this and said, well, if I start applying fracture mechanics, instead of doing stress versus number of cycles, I ought to be doing stress intensity, because that's the more important thing. It's the flaw, it's the stress intensity at the tip of the crack that's going to be driving the crack, not the global stress. And so this is one of the more complete materials. A533 steel is a pressure vessel steel used for nuclear reactors and things like that. Okay, so it's a fairly critical type of steel. There's lots of fatigue data on it. This is one of the most complete curves, and it shows kind of plastic behavior. So down here now on a log scale, everything becomes straight lines on log, right? Except it kind of goes through 3 stages. This is stage 1, stage 2, and stage 3. Very clever, see? Region 1, region 2, region 3, typically called stage cracks. But across here, you do the change in stress intensity. All you do is take this formula. If you're talking about a cyclical stress, which is a change in stress from a low value to a high value, that means your stress intensity is going to change from a low value to high value. And instead of plotting number of cycles, they actually plot crack growth rate per cycle. So I didn't bring it again this time, but remember the little granite specimen I showed you? You need one specimen in theory to generate this entire curve. Now, if I wanted to do the old SN type of curve, I might take 20 specimens, and some of them will be in that machine for 2 weeks, and some of them will be in there for 20 minutes, depending on the stress level I test. And there's a lot of scatter, so I want to run several specimens at each stress level. But I can generate my curve in 1 or 2 months' time with a lot of machining and replacing the samples. However, if I do this, I have a more precise sample to machine, so instead of paying $100 a sample, I'm now paying $1,000 or $2,000 for the machining of the sample. But I can generate this curve in about 2 weeks in the machine, because what I'm going to do is what I'm plotting here is the change in crack length A per cycle. And so I have some little sensor, and sometimes the sensor is nothing more than a little microscope and a light behind it, and I try to measure the crack length as it's moving across. I can also measure the crack opening, because as the crack gets wider, deeper, it opens more and more. So another thing, people use electrical on metals. They use electrical resistance through the thing. They pass a current every now and then, and the cross section that remains has got a higher resistance than if it was a larger cross section. So you use electrical potential drop. You measure the crack growth rate per cycle, and you plot dAdN versus stress intensity, and you get this type of crack growth rate curve. This is the proper way to do it. On the old SN data, the old SN data was kind of empirical. If you changed the part geometry, if you changed the stress type, you could not go back to the same data reliably and interpolate exactly what your results are going to be. What happens now is this is based on fracture mechanics, and I can do it under one type of stress, and I can calculate what it would be under another type of stress, because I have the science of fracture mechanics as the basis for my extrapolation. So down here is small crack growth. There is a limit. As this thing starts to approach, there's delta K threshold. That's the fatigue limit that the other people used to talk about in the old business. Well, it turns out what really controlled this fatigue limit? The small flaws, the small imperfections that were in the material originally. Okay, you might have a flaw in a typical steel if you just go take some garden variety steel off the shelf, you'll have flaws that are around 4 to 10 thousandths in size as a maximum flaw size. Those are just the inclusions in the steel. What's 4 thousandths is about 1.5 human hairs. 10 thousandths is about 4 human hairs in size. Not very big flaws, but basically if you went and put that typical flaw size in and then calculated that stress and the stress intensity, you would find that you were at what's called the threshold stress. The threshold stress, where you don't have enough energy input per cycle at stress intensity to do damage at the head of the crack. In the old days, with the old type of SN type of testing, if you did a particular steel at a particular hardness in an unnotched condition, you get this stress. If you did it in a notched condition with a stress concentration, you get a lower curve. If you're talking about aluminum alloy, they haven't changed the origin. This is on the same scale. So a high strength steel, which 700 megapascals is 100 KSI. Okay, 100. So if you go over KSI, you're 125 KSI fatigue limit. That's a pretty high strength steel. This is not landing gear type of steel, but it's type of strength level that you're approaching the type of strength level that you'd have in a landing gear for an aircraft. Here, if you put a notch in it, you can drop your stress, your allowable stress, by 40%. So someone takes a high strength piece of steel and you put a file notch in it, you're liable to get a fatigue crack. If you go to aluminum alloys, you notice this aluminum alloy, it doesn't flatten out. They're still drawing it with a little slope. It doesn't have a fatigue limit. So that's how we measure fatigue in the laboratory now. And you can go to these plots and you can predict the life of things. In a second, we're going to go through, let me show you one more plot. This is, you still have environmental effects. So this happens to be, this is another pressure vessel steel. It's a chrome moly steel. It's a high temperature pressure vessel, so a boiler type of pressure vessel. And they measured it in moist air, dry hydrogen air, hydrogen sulfide, and frequency from 5 to 50 hertz. And R values is a stress value. We don't have to go through that. But the slope here in stage 2 is always the same. In fact, they call this the Paris law because Paul Paris, now at Ohio State, was the first to articulate this linear region here. The threshold stress can change dramatically. The stress intensity can go from 3 to 7 depending on whether it's dry hydrogen or by air. Which one is this? Moist air. This is moist air. Where's my the hydrogen's up. Dry hydrogen's up there. Let's see, there's also dry hydrogen down here. Down here. Hydrogen actually causes hydrogen embrittlement. Hydrogen can start attacking the steel. And hydrogen sulfide does essentially the same thing. Oh, by the way, when you start plotting this, down here we're at 1 lattice spacing per cycle. So you're breaking 1 aluminum bond per cycle all the way across. You actually start measuring crack growth rates on these things that are less than an atom distance averaged across the whole width of the crack. That's how we do it in terms of measuring it. However, if someone brings me a part and says, why did this thing fail, there's actually an easier way than going through all that. If you want to be quantitative, you can go through all that. But this type of plot's been around for about 30-some years. And I don't even know what the original source was. But you can look at the surface of a fracture, a fatigue, or, well, a metallurgist can look at a fracture and say, that failed by brittle fracture, that failed by overload, that failed by fatigue, this is a creep fracture. Now, they may not be able to say it just by looking at it with their eyes, although often they can, but they basically, I sometimes say it's sort of like reading tea leaves. That kind of says that there's some sort of mysticism to it. And a lot of people kind of think there is something mystic to it, but there is a science behind it, and you have to be experienced with it. But this is one of the tricks that, frankly, I think most metallurgists who do this as experts know this, but for whatever reason, maybe they're trying to keep their secrets quiet. I don't see this taught very much. If I can have different types of stresses. Here we have across here rotational bending, reverse bending, unidirectional bending, tension, tension, or tension compression, and up here, oh, actually, I guess that's tension, tension. Torsion. So torsion, so it's each one above those lines. Different types of stress states. Okay, so you're either pulling on it, bending it, twisting it, bending it back and forth. Well, if you're bending it back and forth, you should get a fatigue crack that starts on both sides. Okay, because you're going both ways. If you're only doing unidirectional bending, if it's just bent down and comes back up, then you're only going to get a fatigue crack starting on one side. So if someone brings you a broken bolt, you ought to be able to look and see whether I've got a fatigue crack on one side or both sides. If it's on both sides, then it's reverse bending. If it's a fatigue crack and it's only on one side, then you say, oh, well, it could either be bending or it could be tension. So it could be either a tensile stress from bending or it could be a tensile stress from pulling, so far as that goes. However, you can then look at other features of the thing. If the final fracture area is large, so this is supposed to be, these little lines here are called the beach marks. As the thing, as the crack grows, it will leave behind, just like a tide going out will leave trash up on the beach. Okay, it'll leave these little marks behind, or the tide going out will sometimes leave ripples in the sand. Most of the time it's smooth, but it'll leave these beach marks. And so that's the region where the fatigue is. There's a different texture there than the final overload. If it's a high average stress, the part has a high stress on it, you'll see a large area. If it's a low nominal stress, you'll see a small area, and the fatigue crack will cover most of the area. Now, if you have something like this, where the fatigue crack, well, actually, let's go all the way over here. The fatigue crack, well, let me back up. There's all kinds of bending of these lines, and that has to do with whether you have a stress concentration, whether you have a notch that magnifies the stress or not. And so this is actually a tensile stress, but you end up with a final fracture area that's right here. Very small final fracture area. That means the loads on this thing in normal service were very, very small. If the loads were very, very small, well, I should have been at my fatigue limit, right? In terms of the nominal stress, that's true, but I had a stress concentration which magnified them. So I still get once or twice a year, but I used to get half a dozen times a year, these insurance adjusters, someone's fishing boat. And I don't get it as often because we don't do as much fishing in New England anymore. But they'd bring in a broken propeller shaft into my office and say, why did this thing fail? Well, most of the time it was fatigue. And the first thing I would look for is, was it a large final fracture area or a small final fracture area? Well, most of the time it was a properly designed propeller, right size, and it was a small final fracture area because you want to design it so it has low stress and it's immune to fatigue. And let's face it, propellers get lots of cycles on them. But then, in almost all cases, I could see evidence from the shape of the fatigue crack that there was a stress concentration. And it might be a keyway, it might be a notch that causes a stress concentration. There's lots of things that cause stress concentrations. This should be in your notes somewhere, but basically, whenever you have a change in section thickness, you'll have a concentration of the stresses. And you can actually draw lines. If you really want to be precise, you can solve Laplace's equation for the stress. Okay, and it will show you that basically you'll get nice little contours, and wherever the lines congregate, okay, or tighten down, that's going to be a region of stress concentration. So you can have threads, you can have notches machined in, you can have fillets, you can have keyways in your thing. So many times these things might be because of some keyway. What the surveyors usually want to know is because the guy will usually say, well, this is covered under my insurance policy because I hit a rock. You know, it wasn't marked. You know, I ran aground on something on an unmarked shoal, and that's covered by my insurance policy. It's like having an accident in your car when someone else hits you, right? So they want me to say, well, what started this? Well, you have to kind of read the tea leaves here to figure out what started it or not. And to give you an example, not from boats, but I had a guy come to me. Actually, it is from boats, but it's not from a propeller on a boat. A guy, an MIT grad, alum, came by he works for a company that makes parts for sailboats. Only he makes very special parts for very special sailboats, and some of them are America's Cup yachts. And so this actually is part of a hydraulic cylinder that they use to raise and lower the sails for America's Cup. And it turns out, the reason I asked him if I could have the part when he was done with it, the broken part, it's sort of interesting because he says, well, in the America's Cup business, it's all competition. If parts don't fail every now and then you made it too heavy, is the philosophy. So you want to thin things down. You're so competitive. You're going to make things so thin and so lightweight. Every ounce makes a big difference that you will design them right to the limit. And the problem was, this was like the second or third failure, one of these things as a designer of parts. He didn't particularly like that, mostly because they used 7,500 PSI hydraulic pressure to lighten the weight of the system. They go to very high pressure systems. If you know anything about hydraulic systems, well, if you know anything about high pressure water washers nowadays, 3,000 PSI is a high pressure system, right? They go to 7,500 PSI. In these things. And to make it lightweight, instead of making it out of steel, which is what most people would make a hydraulic cylinder, when you're dealing with people who have more money than brains, and it typically costs $50 to $100 million to compete in the America's Cup nowadays. And it's only people like, who's the number 2 guy at Microsoft that bought the Seattle Mariners? Paul Allen. Paul Allen, didn't he sponsor America's Cup yacht or something, I think? But there's a guy, Koch, K-O-C-H, whose father started a big company that's a multi-billion-dollar company. One of the Kochs came to MIT, got a master's degree in chemical engineering, and he gives MIT like $20 or $30 million a year. So he's fairly generous, but he's worth billions. And a few years ago, he decided to compete in the America's Cup, and he budgeted $60 million for this. And he had a professor over in ocean engineering designing the yacht for him and things. And I think he actually, I can't remember if he was America 3 or whatever the name of his yacht was. But it got to be so expensive that as an MIT faculty member, I got this glossy brochure asking me if I wanted to contribute. And I thought, now why should I be taking, I don't make $1 billion. I'm not worth $1 billion, okay? And here I have a multi-billionaire asking me for donations for the America's Cup. I actually did donate because the professor over there in ocean engineering had a welding problem once, and so I went over at 6 o'clock in the morning. There's not very many of us on the faculty here at 6 o'clock, but he's one of them, and I'm one of them. And I basically gave free consulting. How about that? That was my donation. But I didn't see why I should be donating cash to a billionaire just because he went over budget. But nonetheless, getting back to this thing, it had failed. It failed in fatigue. I looked at it in my dining room and I said, oh, well, there's the fracture origin right there. When I pass it around, you can see the fracture origin because I marked it right here. If you look very carefully, you'll see a little thumbnail notch, which is typical. And you actually can see it in this light. The other day in my office, which I have brighter lights, you couldn't see it, but there's a little region where you kind of have radial flaws growing there, and here you have the fatigue crack lines. Actually, this is the fatigue crack, okay? You can't see, but if I went into an electron microscope, I could find the beach marks there, but you'll see kind of this little thumbnail shaped region if you get it at the right light, area of the light, and it's literally, I'd prefer you not put your thumbnail over it, but it's about the size of a thumbnail. And it goes about 80% of the way through the thickness of this thing, okay? So that was the problem. I said, oh, well, it's a fatigue crack. This thing's messed up at the bottom anyway. Well, I'll have to redo this some other time. but don't use green markers. The original design was 7075 T6 alloy. So I go and I look up, well, I'm told it's 7,500 psi operating pressure. It's 12,000 psi proof test pressure. So you got a design pressure, which is 75, that's what you're going to operate at 7,500 psi. But you want to check each part to make sure you didn't manufacture it with some flaws. So you proof test it. You actually load it up to 12,000 psi. And if it sustains 12,000 psi one time, then you have some assurance that, well, hopefully it won't fail when it's only under 7,500, unless, of course, you get a fatigue crack throw. That happens to be 100% of the specified minimum yield strength. When they went to 12,000, that's how they selected it. But they're going to operate at roughly 2/3 of that. And that seems all right. Well, it turns out that it cracked. And in fact, it cracked in a brittle fracture such that, you know, they couldn't get the sail up and they had to have a spare on board. Why are you trying to keep the weights down, you know? Although I guess maybe they take the spares off when you're really in competition. This was probably just in training. In any case, the redesign that I suggested was go to 7075 T73. Now remember that little aluminum washer I said from the helicopter I bought? This was because I had worked on that. And I knew that the 7075 T6 was susceptible to stress corrosion cracking. That looks like a stress corrosion crack to me, but we won't go into that. And so I said, well, go change from the T6 heat treatment to the T73, but the problem is, and you can't read this, is the yield strength of the T73 is down from 73 KSI to 63. However, the toughness goes up from 26 KSI square root of inch, kind of interesting units for the stress intensity, but if you go back and look at the equation, if this has units of stress, PSI, and that's the square root of inches, this has units of stress, PSI square root of inches, or KSI square root of inches. So you get a significant drop, a 15% drop in yield strength, but you get a 15% increase in toughness. And they decided to add a little weight. They went from 3mm wall to a 4mm wall approximately. And it turns out by doing that, if you go through the stress intensity calculation down here, you'll find that the critical flaw size to break in the original design is about 2mm. You look at that thing, that crack goes about 2mm down. We just verified that these material properties I looked up in a handbook for the original 7075 T6 are correct. And you can't read this very well, but if you go through this, you find the critical flaw size is about 4.5mm. And the thickness is only 4mm, or just under 4mm. That means that you actually get leak before break. You actually squirt out a little bit of oil before you get the whole thing split in two. And in fact, that's one of the criteria we like to have when, safety criteria, in designing things. You like to design pressure vessels so they leak before they go boom. Makes sense, right? So you use fracture mechanics, and basically by changing the heat treatment on this, changing the thickness of the wall a little bit, they were able to make one that when it fails, is not going to fail catastrophically, and you're not going to be able to put your sail up, or you're going to have to, you know, you might lose the race, right? If it fails catastrophically. If it's just shooting out 7,500 psi oil, well, don't stand in front of it. You might cut your finger off, right? But you know, you may be able to still get your sail up if you got a big enough pump behind it, right? If it's a small crack or a small leak. So. Let's see, what else do we want to say about any of that? So that's leak before break. You can go through, the point is you can go through, you can analyze failures quantitatively, you can look at fractures, you can, if you're experienced, you can look at a fracture and say, that's why it failed. There's lots of useful things you can do with this. For example, a couple of years ago, a graduate student came to me and he had bought an engagement ring for his fiancee. And is your old roommate? Oh, I didn't know that. Well, he came to, I was department head, and it turns out, of course, it had a diamond, and it had the little post in the gold setting, and the diamond fell out. I mean, fortunately, they didn't lose the diamond, but he wasn't very happy, and his fiancee was not terribly pleased that she couldn't go show off her diamond to her friends and stuff. And so he came to me. He actually first went to the jeweler and said, I want you to fix this. And the jeweler said, it's not my fault. So we put it in the scanning electron microscope. I did all this for free. I do some pro bono work. And I ended up writing him a report showing that they had folded it over. They basically just kind of have these little metal posts, and they just kind of bend the metal over, and the stuff had been too thin. They had machined it incorrectly. And so, actually, I got a nice email from him about six or 8 months ago. No, I know.
Yeah, and then once you did that, they took care of the problem.
They got my letter from an MIT professor. They decided, that it was easier to be nice to him and do what they should have done in the first case. When I was a graduate student, someone came to me, another graduate student came to me because he was shifting on his, I think he had a Ford, and he had a shift in the center console, a manual transmission, and the thing just broke off, okay? And I looked at it, and sure enough, it's a fatigue fracture, and it was because, in this case, they had just screwed the thing in, and it had failed at the stress concentration, but they had also plated it. And if you remember that plot I showed you, they electroplated it. They chromed it, right? In this case, by looking at the fracture, it was you shouldn't have had, when you're just shifting, you shouldn't have any high stresses. This is like a 1/4-inch piece of steel. But notice what happens if you have hydrogen, okay? So they actually had a hydrogen crack, or they had hydrogen embrittlement, which lowered the threshold stress for these things. And I actually wrote a letter at that time. I did all this pro bono. However, Ford, if I remember who it was, might have been GM, refused, even because I was just a graduate student at the time, right? They figured they could fight with a graduate student, I guess. So there is an advantage as you get older. People don't want to fight with you as much. And I think he actually had to, it was like they wanted $50 to repair this thing or something. But to a graduate student, when back then $300 a month was a graduate student stipend, $50 was a lot of money. It's still a lot of money for most graduate students, but it was even more back then. And he never could get them to pick up the cost. So whenever you have a failure, don't throw it away. Look at it and figure out why. So whenever something breaks at my house, I kind of go and I look at it. And you'll find when you get to adhesive bonding part of the lecture, you'll hear my story about when your children bring you a broken plastic toy and say, Daddy, can you fix this? Or Mommy, can you fix this? Well, it turns out if it's made out of plastic, the answer is probably no when you get to adhesive bonding. But actually, even if it's made out of metal, but you could probably solder it. You may not be able to adhesively bond it to fix it. Okay. What else do we want to do on fracture? Okay, residual stresses. How about residual stresses? Do we have time for residual stresses? We should. One of the things that causes lots of failures and people don't often think about is the fact that parts can have residual stresses in them. And so they design it for a low enough stress so they shouldn't get fatigued. But something else happens. The case of that washer in the helicopter, that stress corrosion cracking, they didn't have just the fatigue stress limit, they had corrosion going on, which dropped the fatigue stress. Typical fatigue stress for the 7075 T6 aluminum should have been like 35 KSI for a practical fatigue limit. It doesn't have a fatigue limit, but you ought to be able to operate that. Since it's got 73 KSI strength, you ought to be able to operate it at 50% of that, like 35 KSI. But in fact, it failed at 8 KSI. Why? Because you had corrosion going on too. So stress corrosion cracking can be very insidious. Usually fatigue, as long as you're at stress levels below half, But stress, corrosion, cracking, sometimes you have to be at stress levels only 10% of the strength of the material, which is why you really want to design away from that. That's some of the problems that General Electric had. I did mention the General Electric problems in the nuclear reactors, right? The stress, corrosion, cracking they had, and cost them a couple $2 billion. So you got to control flaw sizes, you got to control stress, you got to control your environment, you have to design things for the proper temperature and whatnot. But you do all those things, and then things still fail. And it's because a lot of times the stress that's actually in the part is not what you thought it was. Sometimes that stress is higher because of stress concentrations, the little notches we talked about. But many times it's because you have locked-in stresses within the part that you didn't know about or didn't suspect. And in fact, that washer that I talked about, that helicopter washer, actually had residual stresses. Some of those parts just failed on the shelf. They'd never been put in a helicopter because when they heat treated the aluminum, they heated it up and they quenched it in water. And when they did that, they introduced residual stresses in the part. We measured residual stresses of 11 KSI, and the stress, corrosion, cracking stress level was only 8 KSI. So it just failed. They just failed sitting on the shelf. So they weren't happy with that. Well, residual stresses can come from a number of things. They can be mechanically induced. Sometimes you intentionally induce them mechanically. And actually, we don't have time for this. I'll tell another little story. Once when I was, my first summer job between my freshman and sophomore year here, I worked at the Naval Air Rework Facility. And if you do a weld repair on titanium to go into the jet engine, they had a requirement, because you get thermal stresses, residual stresses around that weld from all the heat of welding, and things contract. They heat up at different rates and they contract. And when they do that, you end up with welding residual stresses. And so they had a spec that you had to stress relieve the part by putting it in a furnace at a high enough temperature to cause the material to creep intentionally in the furnace in a controlled way and allow the material to relieve the residual stresses. And we'll talk tomorrow about those types of residual stresses and thermal stress relief and stuff. In any case, this is during the Vietnam War, and they had a need for lots of jet engines over in Vietnam. And so we were repairing and rebuilding these jet engines for the Navy. And they had assembled one completely, and they found a crack on final inspection. They found a crack in one of the inlet compressor blades. So this is the fan blades you see in the very beginning. In order to do this, they were going to have to take this out and take it back through heat treatment, and it had internal cooling in the titanium, and they had actually. I don't know if it had internal cooling, but it actually had a polymer that had been put up in there. It was going to take a month and a half to disassemble this, bake out the polymer, weld repair it, stress relieve it, put the polymer back in, and reassemble the engine. And they needed engines over there. And so they decided they were going to weld it in place. And so, but they still needed a way to stress relieve it. We couldn't do thermal stress relief because you can't put the whole engine into the furnace. You could, but you wouldn't be a very good engine because there's other parts, rubber parts, O-rings and stuff wouldn't survive. So they decided that they wanted to do mechanical stress relief. And one way to mechanically relieve things is to do peening. You basically take little steel shot, BBs of steel, and you shoot them at the surface. And you pound the surface and deform the surface, and that creates compressive stresses on the surface that will stress relieve the weld and prevent fatigue cracks from growing, because I now start with a compressive residual stress on the surface rather than a tensile one. So we went out and actually they didn't want to shoot BBs into the engine, so they basically just made up a little tool with a little ball on it, and then they had a vibrating air gun that basically just beat this little tool, spherical ball into the surface to peen the surface. So it's sort of like shot peening. And I was the engineering aide that had to go out there and witness the guy doing this. And you develop what's called an Alman gauge for this. This is the standard. You take a piece of steel that's flat, and you peen the surface, and after you peen the surface, the thing will bow up because, it'll bow up because you're going to learn that whatever stress you induce in it while you're working it, it'll go in the opposite direction when you're all done. By compressing the surface, you expand the surface, and so when you're all finished beating on it, it will bow up. And you measure the height of that bow, and it tells you how intense your peening is. That's actually how they, if you're doing a shot peening in a spray booth and shooting BBs at the thing, you just put an almond gauge in there, and you take it out, and you see if it bent the right amount when you're all done. So I had to check the almond gauges, and we found that this guy operating this thing and pressing down, there was no reproducibility whatsoever about the almond gauge height for how long he peened this thing. But the boss in engineering says, well, go ahead and do it on the real thing anyway. So they well repaired it, and the guy beat on it, and I witnessed his doing it. And then I came back in, and the head of engineering says, sign this. Because you had to have 2 signatures on this was a deviation from the standard procedure. You had to have 2 signatures, and I said, well, what am I signing? He says, oh, don't worry about it. If this plane goes down, you'll be in jail within 24 hours. I thought, oh, well, that's nice. In fact, that is true. I mean, there's certifications on things, and you're held legally responsible. And he says, no, just go ahead and sign it. So I was 19 years old. I went ahead and signed it. And then he signed it. Fortunately, he was willing to sign it too, right? Because I was just a 19-year-old. I didn't know. And fortunately, I'm sure that aircraft, that engine is no longer in service now, so I did not go to jail. And I assume it didn't fail because of this weld repair. And we were doing the best job we could. But it kind of tells you that sometimes you just have to take some risk. Most of the time nowadays, in current litigation environment, people would never take such a risk. Okay, but I didn't know. I was only 19 years old. And, hey, what could they do? Shoot me? You know, it'd all be over then. Okay, I'll talk to you tomorrow. Thanks.